Good afternoon. I'm Lisa Perazzoli, and I'm a Senior Product Manager with Amazon Redshift. I'm delighted to be here this afternoon with Equinox Fitness. And in just a few minutes, Ryan and Elliot are going to talk about their data journey and how they use Redshift as their modern data warehouse and S3 as their data lake. So, by a show of hands, how many of you are already using or have played around with Redshift? Great, it's good to see that most of you are using it, and I'm excited to share how the service is evolving to meet your needs. So, Equinox Fitness is a good example of a forward-looking company that's evolving their analytics strategy. Before Ryan and Elliot talk about their use case, I want to take a step back and talk about data warehouse modernization. We hear firsthand from customers that you want to store unstructured data at exabyte scale. This includes machine-generated data like log file and clickstream data. You want a single view of all of your data in a unified space and an easy way to catalog and search all this data and then do analytics on top of that. You want to do new types of analysis on your data. You want to move from answering questions about what happened in the past and move towards answering questions about what could happen in the future. So traditionally, if you started doing data warehousing back in the day, you had your SAP database and your Oracle data warehouse and a pipe that moved data between the two. And you updated it maybe once a week, or if you were really cool, once a night. And for the most part, it worked pretty well. So what's causing people to look at a change? Well, across a large number of organizations, data typically grows 10x every 5 years. So you need a system that scales up to 1,000x. And that leads to a whole new architecture. We also hear about new requirements from you because of the increase in all of this data. You want the ability to store and run analytics on unstructured data at exabyte scale. And you've probably realized by now that the traditional data warehouse was not optimized for storing all of this unstructured data. Also, there are more data types that exist today than ever before. You want the ability to incorporate machine learning, and this includes data generated from IoT devices, log files, clickstream data, data processing, and real-time analytics. The traditional model could only accommodate reporting and ad hoc analytics on relational data. And then, because of this, we've also seen a lot of new frameworks that have all taken a stab at solving part of this problem. And you really want to be able to use Hadoop frameworks to complement your data warehouse. So, what do we even mean when we say data warehouse modernization? Data warehouses and data lakes are coming together. However, you still want to analyze your data in a highly optimized analytical database that has tight integration with the data lake. There are 4 key pillars that we see for a modern data warehouse. First, it should be designed to support rapid data growth and analytics over a variety of data types. It should scale up for increasing analytical demand and scale down to help you save cost. It should do this both automatically and on demand. It should be consistently fast, even with thousands of users and concurrent queries. And a modern data warehouse should be easy to use. You shouldn't have to waste time on administrative tasks. And you also want a data warehouse that extends directly to your data lake. You should be able to query across the data warehouse and data lake. Amazon Redshift is a fast, scalable data warehouse that makes it simple and cost-effective to analyze all your data across your data warehouse and your data lake. Redshift delivers fast performance by using machine learning massively parallel query execution, and columnar storage on high-performance disk. You can start small with a few hundred gigabytes and scale out to exabytes. And unlike a traditional data warehouse, you don't have to commit to buying capacity and can easily try out Redshift for new use cases. There are over 10,000 organizations that trust Redshift as the foundation for their analytics platform, from startups to enterprises across nearly every industry. And you can use Redshift with the third-party tools you already use today or the tools you plan to use in the future. One differentiator for Redshift is the pace of innovation. These results are due to our focus on performance. We released several under-the-hood enhancements, such as improvement in resource management, query planning, commit performance, and short query acceleration that transparently boosted performance over the past year. Based on these improvements that we've made to Redshift, we've experienced a 3x improvement in speed compared to where Redshift was out just 6 months ago. And we're always looking for ways to make Redshift even easier to use. We recently launched Query Editor, which allows you to query data in your Redshift cluster directly from the AWS Management Console. This provides an easy way for users to run SQL queries without having to install and set up a JDBC ODBC client. And the query results are instantly visible within the console. Advisor is another relatively new feature that provides automated recommendations to help you optimize database performance and decrease operating costs. Advisor is available via the Redshift console at no additional charge. And you can think of Advisor as a personal database assistant that generates tailored recommendations to your operations and cluster configurations based on analyzing your cluster's performance and usage metrics. We're also working to move towards a zero maintenance world. So we want to completely remove the need for you to do any tuning or administration. With the new Auto Analyze feature, Redshift will automatically update the table statistics on your cluster. And then the vacuum command reclaims space in the specified table or database. And previously, this was a manual operation that you had to go in and think about. And what we're doing now is we're planning to automatically run the vacuum operation in the background so you don't have to spend time thinking about it. And we're also automating the workload manager concurrency setting that determines the number of parallel queries. So it will automatically deliver optimal throughput for your changing workloads. And then many Redshift customers have workloads which need additional compute and storage resources to meet their changing and growing workloads. So for example, you might have an ETL workload that runs for certain hours in a day, or you're going to have month-end reporting, and you know you're going to have a demanding workload and need more resources. With Redshift, you can scale quickly in a couple of ways. First, you can query your data directly in your S3 data lake with the Spectrum feature without needing to load it in the cluster. So this flexibility lets you analyze growing data volumes without waiting for ETL jobs or adding more storage capacity. We also recently announced Elastic Resize, which is a new feature which allows scaling your Redshift cluster up or down in minutes to get better performance and more storage for demanding workloads. And it removes nodes when they are no longer needed to save cost. So when you enable Elastic Resize, Redshift adds additional nodes to the cluster and distributes the data across the new configuration within minutes. This feature is a significant improvement over the traditional classic resize, in which you had to provision a new cluster, and this could potentially take several hours. With Elastic Resize, you can easily increase the size of your cluster's compute and storage and quickly process complex workloads and decrease your query response time. Concurrency scaling is another new feature we recently announced, and it adds transient capacity when needed to handle heavy demand from concurrent users and queries. So a typical data warehouse has changes in concurrent query usage over the course of a day. And with concurrency scaling, you simply configure how many clusters you would like to use in the AWS Management Console, and Redshift automatically ensures they're ready to handle additional users as they arrive. And then, due to the performance improvements that we previously discussed, what we saw was that 87% of the current customers don't have any significant query wait times, so they don't really need concurrency beyond what the main cluster already provides. But for every 24 hours that your main cluster is in use, you'll accrue a 1-hour credit for concurrency scaling. What this means is that concurrency scaling will be free for more than 97% of customers. And then keep in mind that it's not just about the data warehouse, but also about the transition to data lakes. Moving to a data lake can have the greatest single impact on your long-term storage, management, and analysis capabilities. Data lakes have caught on really quickly, and for good reason. They allow you to store all of your data in a unified, single place where you can collect and store any amount of data at any scale and all at a low cost. One of the advantages of a data lake is that you can run a variety of analytic tools against it. So I like to think of a data lake in terms of concentric circles. Let's assume that you put your data into S3 or an object store of your choice. You want a system that can ingest quickly, and there are a lot of ways to get data into S3. Once your data is in S3, you want a way to easily understand what data you have in the lake. And we offer a service called AWS Glue that automatically crawls and catalogs your data, so you're not stuck doing all of this manual data entry. And then once cataloged with Glue, your data is immediately searchable and queryable. So once you know what data is stored in the lake, you can start to run your query processing engines on top of that. And it might be a service like Athena for ad hoc queries that are done once in a while. You might use Amazon Redshift for your bread and butter data warehousing. It might be EMR to process complex Spark and Hadoop jobs. The differentiator for a data lake is that it really allows you to run the best analytic tool for the job, and you want that flexibility. And then, most importantly, you want to ensure that your data lake is secure. And with AWS, security really is our top priority. With the S3 data lake model, you can encrypt all of your data with AWS KMS. And then you've probably all heard the phrase, data has gravity. It's hard to change once you have a lot of data. As you move to a data lake model, you want a system that lets you store your data in open formats, JSON, Parquet, ORC, etc., and not in a vendor's proprietary format. You want to use open data formats and open APIs. This is because the decision you're making is a long-term decision. Open data formats allow you to query the data with the best tool for the job. They also eliminate data silos and lock-ins. And they allow you to bring in new analytic engines or change your engines, ensuring that your solution is truly built for the future. Customers choose Amazon Redshift over traditional data warehouses because it really does provide fast performance at any scale for any workload complexity, and it provides deep integration with the data lake. So with that, I'd like to turn it over to Ryan and Elliot from Equinox Fitness to talk about why they chose Amazon Redshift as their data warehouse and S3 as their data lake.
Thank you.
Thank you.
Hi, everyone. I'm Elliot, and this is Ryan, and we're with Equinox. So a little bit about Equinox, for those of you who are not members yet. So Equinox is a company with integrated luxury and lifestyles offerings centered around movement, nutrition, and regeneration. So that encompasses the brick-and-mortar Equinox brand, which is our flagship, Blink, which is another fitness offering, Pure Yoga, Soul Cycle, which is a boutique high-end studio cycling experience. Furthermore, in Equinox hotels. And we'll be opening our first hotel in Hudson Yards in New York City in this coming spring. And we have several other fantastic properties in development as well. So all totaled, we operate approximately 250 locations across every major city in the US, as well as Canada and the UK.
So you may be thinking, you're a gym, how hard could it be? You have people who come, check into the club, lift weight, put it down, sometimes very loudly. We apologize to Men's Warehouse for shaking the building sometimes. But ultimately, Elliot, how hard could it be?
Yeah, so we're a prime example of you can make anything complicated if you try hard enough. So aside from our scale, again, like 250 brick and mortar locations, 98 just for our flagship Equinox brand, which has 14,000 employees. Each one of our gyms has a series of lines of business within it, over a dozen lines of business, ranging from personal training to group fitness to membership to spa, where we operate the nation's largest corporate operated spa chain. We have heavy investments in digital, and we have all the supporting functions that you'd expect from a large company, from CRM to finance to member services.
And not only that, more and more of it is becoming connected. We have our digital products, which are servicing end users. So these end user applications are used by people in corporate positions. So we have people in the gyms who are using them. Maybe it's the front desk, maybe it's our personal trainers, maybe it's somebody who is a membership advisor or works in the spa. But not only that, we also have our members who are using our applications as well. And in addition to that, we have connected equipment in the gym itself. So Pursuit, which is our gamified cycling experience, is a spin class that actually collects data from the bikes in real time and shows the performance on screens for friendly competition. In addition to that, we actually have a freshly launched digital assessment program where you can get a fitness assessment in a room with a digital experience to accompany it.
So a little bit about our data journey, and then we'll hop into the new stuff. So, our first data warehouse was named Life. Our company logo is it's not fitness, it's life. It was created and launched somewhere around 2008. Like most traditional data warehouses, it was cylindrical in shape. It was a very traditional data warehouse. We used Informatica. It ran on SQL Server. It was rigorously Kimball. We followed the book and made sure we did everything, as perfect as possible from a Kimball methodology perspective. And the results were pretty good. It was a solid methodology, decent technology at its time. Reporting was reliable. We had a growing analyst community and later data science community. We were able to do really cool things in terms of advanced CRM, email marketing, personalization. But all good things come to an end. Sometimes life is bad. We ended up with a lot of direct integration into our data warehouse. The reason this is because like many data warehouses where you end up with a lot of tight coupling with other applications, it's the first place where facts about your customers are born. It's the first place where data is brought together from various systems, so people want to reach in from different applications and use that data and maybe use it in a way that you didn't intend. That along with a difficult SDLC, so we weren't able to really adopt like modern like CI/CD principles because we had fixed infrastructure, made it very difficult to do automated testing. Most of our testing was manual and exploratory. This plus the tight coupling where our partners didn't want us to change our system, we ended up with a lot of functional debt. And then we had the new problems of not having a place to put new data from our clickstream or our cycling logs or different marketing data that we had access to. And this created inflexibility for our analysts and our data scientists. And also we're just running like expensive commercial software, a decent amount of expensive commercial software. So we decided to spend more money on a commercial solution. So about 5 years ago now, we purchased Teradata to really help with some of our workload problems, as well as to help us mitigate the fact that we had an overgrown, like very large multi-terabyte SQL Server database. So we launched several apps in beta, and we just ran into like a lot of challenges. First, it was pretty difficult to build on Teradata. We found that you needed a lot of platform-specific knowledge. A lot of our engineers had to really figure out how to interact with the platform. We were at the point that we were going to hire like a Teradata DBA. And we found that we had like a lot of problems with integrations as well. We wanted to integrate with the cloud, kind of be able to integrate with other systems very easily, and that wasn't possible without buying more expensive integrations. And overall, the system was very expensive aside from the initial product purchase, which was very expensive. The maintenance and licensing of Teradata is quite oppressive as well. So we decided to back up for a second and think about what we're trying to accomplish, figure out if this is the right approach after we got so far into the project. We decided that we wanted to build technology that differentiates and provide business value. We just didn't want to get stuck doing an infrastructure project for several years that nobody in the business really cared about. We wanted to reduce costs and go all in the cloud and adopt modern engineering principles. The rest of our tech organization had already started to do this with heavy investments, and we were not. So we wanted to make everything scalable. We wanted to use ephemeral resources, get into distributed databases, and worry less about individual servers.
So at this point, Elliot, what if we just threw everything in a data lake and made everything lake bind? Do we even need a data warehouse? Would that work?
Very good question. So, I tend to think about data warehouses versus data lakes like this. So data lakes are really good for large immutable data sets, semi-structured data, and unstructured data sets, log data. Data warehouses, on the other hand, are I find to be useful for high SLA reporting. They provide generally better performance. They are very developer and analyst friendly. They are very familiar, very easy to work with. In the case of Redshift, it's Postgres-like. And it's efficient for specific types of pipelines. So if you have a data pipeline which is mostly immutable log data, clickstream data lakes are very easy. If you have customer data and you have systems that allow update statements on the data, you have mutable data, that stuff is pretty challenging to accomplish in blob storage within a data lake. So mutable data is very easy to work with within a data warehouse application. So we were at a crossroads. We decided to do a 2-week proof of concept using Amazon Redshift and S3. I had a decent amount of experience with Amazon Redshift and S3, so it was an obvious choice for us. So we replatformed one Teradata app to an AWS solution in our spare time on our own, and it worked. It was successful, and we were really happy with the results. So we decided to make a decision, and unfortunately, we couldn't find any buyers for our Teradata cluster anywhere, and it ended up going to technology salvage. So a little bit on our move to Amazon Redshift. So our new system is called Jarvis. It is a data warehouse and data lake system, as well as a series of data services and data marts. So our main data warehouse is platformed on Amazon Redshift. That's why we're here. Our data lake on Amazon S3, and using a number of services to process and interact with data.
And so the way that we've laid this out is, from left to right here, all of the data that we're bringing in, we have a number of different methods on how we actually want to deal with that data. So in instances where we want to essentially lift that data and move it over to Amazon Redshift, we use our own Maximilian platform, or we'll use Informatica for that. And the main goal there is to ultimately use ELT, so that once it gets into Redshift, we can then transform it and then put it in another table there. For things that are larger crunches, what we want to use here is we want to take that query capacity away from Redshift and say, let's actually do that on EMR and run it there. And so we'll transform it in EMR and then place that in Redshift. For other data sources where we leverage the data lake, we'll go ahead and move that data into the data lake, and then we can also provide some transformations using Redshift Spectrum. And then at the end here, we have the presentation layer. So these are services or applications that you're going to want to reach in and get that data. And so what we've essentially done here is created agreements or contracts with these applications to say, here is the mart, the data mart, the API, the Postgres database that you'll want to use based on your specific use case. And so those are the things that we'll set up, and we'll place data there so they can reach into those services instead. There are some instances where our analysts will go straight into Redshift, or we'll have BI tools read from there. But ultimately, we really try and focus on creating those contracts and agreements. And underlying all of this, we have our data monitoring and quality services that we've built.
So in terms of Redshift benefits, obviously cost effective. So just not considering the initial purchase price of Teradata, we are essentially paying 1/10 of the cost of Teradata and SQL Server just in licensing and maintenance alone, so huge cost savings. We've had very low barrier of entry for developers and found that Redshift is very easy to maintain. We do not have a Redshift DBA, and our developers are very productive. It's very familiar to them. They find it very easy to work with. Fast in performance, so we had workloads that were running in SQL Server or Informatica that were taking 4 or 5 hours to complete. These now are done in Spark, in EMR, as well as Redshift Spectrum. The pipelines are taking at max like 15 minutes for our biggest crunch. Something that we really love about AWS and about Redshift is they create an API to back up every service that allows you to interact with it. So we found it very DevOps friendly, and we're going to talk a little bit about the automation and stuff that we've been able to do with this. But we're able to do really interesting things in terms of multi-cluster deployment, automated regression testing of our data platform, and just automating things to make things really efficient and reduce our sysadmin overhead. And then, of course, like other things in AWS, integration with other AWS services. So there's a lot of really easy integrations that you can do with various AWS services with Redshift.
And so with S3 and with our data lake, we just wanted to highlight some benefits that we've seen there as well. So besides being highly performant and low-cost blob storage, it actually is a great functioning analytics store when you have good strategies in place. It's very tempting to, once you throw data in there, want to throw everything in there, but you just need to make sure that you have good strategies, and then you can really make it a functioning analytics store. The other thing is that it's extremely flexible. So when you're bringing this data in, you can describe it at any point that you want. As long as you're bringing it all in, you can use a late bind strategy and describe it at a later point. For setting up external tables and making it queryable data, it's actually a very fast setup for it. We've actually had instances where our data scientists have asked for new data, and we've been able to set up an external table on top of that data within a matter of minutes. And then, of course, for any disaster recovery, it's actually very easy to set that up. It's just a configuration option that you can set on the bucket itself. And so I just want to describe some of the data that we actually have in the data lake. The very first one here is what really kicked it off for us, and that's the clickstream data. Originally, what we had done is we had set that in Redshift itself, and then we said, here's about 20 to 30 columns worth of data that the analysts can use to enrich their other data sets. What we found is that they actually liked it so much they wanted more, and this caused us to have to essentially add more columns in and then recast that data historically. But the older the data got, and the further back in time we had to recast, it just added on and on to it. So what we did is we ended up putting that into S3 and then using that late bind strategy to say, okay, we already have all the data there, let's go ahead and describe a new column. The other benefit was anytime there was an evolution in the schema, we would have to find a way to figure out how to deal with that. We actually had an instance where Adobe Analytics, our clickstream provider, deprecated a column, and then it ended up changing the shape of the data itself. And so the way that we had the data described, it was now offset. And so that was something we had to accommodate. And so because of these problems that we kind of had and we went to the data lake, we actually found a lot of success with it, and then we started putting more and more data in there. So this includes our pursuit cycling logs that I described earlier, which this one's actually really cool because each of these bikes is sending about 6 data points per second. So across 40, 50 bikes in a class, for about 45, 50 minutes, happening multiple times a day across 98 clubs, you end up with hundreds of millions of data points there. We're also bringing in logs from our club management software and really any other data services that kind of enhance what we do at Equinox. And so I actually want to take you through a data lake setup example. This is what we did for our clickstream data, and I just want to show you how easy it really is. So just to take a quick step back, the toolkit that you'll be using is just a couple of things here. So at the very bottom of it, the foundation of everything is going to be S3. So once that data is in there, you can then say, I'm going to describe this data in AWS Glue. And once it's described, you actually have a number of tools that you can use in order to query the data. That can be Amazon Athena, which is a serverless querying tool. It can be Redshift Spectrum, which allows you to query data in S3 in Redshift. Or it can be Amazon EMR, which is Elastic MapReduce. And so getting that data in, this was actually a very easy setup for us. So Adobe Analytics had an option to send data to S3. So it was just a matter of specifying our credentials and telling them which bucket to send the data to, and then we got the files daily. We weren't really sure how the files were going to get sent to us. So what we ended up finding out was that each of these files that came in, there would be multiple sets of them. So we had multiple data files, we had multiple lookup files, and then we had a manifest file that told us everything that they sent, which was actually pretty nice for us. So what we decided to do is we said, well, let's go ahead and land everything into our data lake. We'll send it in raw. And then we'll launch up EMR to read that manifest file, because that's going to know each and every file that it needs to access. From there, it's going to look to collapse everything into one pristine data file and save that in our data lake. And so we decided to save it as Parquet because it's a self-describing columnar storage file format, very similar to how Redshift stores its data. Something that we also decided to do here was leverage a partitioning strategy. And so you can see that it's a key value pair, and that's actually how the folder's named. So because we're getting these files daily, that's how we partition the data. And so we did DT for date, and that equals the year, month, and day. And the whole benefit here is that when you partition your data, you're actually reducing the amount of data that needs to be scanned. So when you query it, you're not querying terabytes at a time, but maybe mere megabytes or gigabytes. So once that data is in S3, you need to describe it. This was a two-part process that we had to do. And so what you have to do first is just set up your database. You can just click Add Database, type in the name that you want, and then hit Save. The next step is to actually define the data. So through the interface itself, it's a mere 4 steps. You can just hit Add Table, and then point that data source to a bucket in S3. And then you can define your schema. So you can define the columns that you want and the data types for those columns. And as mentioned, if you ever want to add one, it's very easy to do so. You just go in, edit the schema, add one, and then hit save. And then it becomes queryable automatically. You'll notice at the very bottom here, the very last item actually has a value in that last column on the right. And that just says partition there. And so what it actually is it's DT. And so even though DT wasn't actually in the data itself, it becomes a column which you can query on because it's in that folder structure. You can also create external tables through Amazon Athena or through Redshift itself, but just running a create external table command. And so this was our full description of our table for clickstream. So we had the name of the database, the name of the table, the location in S3 that we pointed it to, and then each and every one of our definitions. At this point, we have about 66 columns defined. But ever since we started moving over to this, life's been a lot happier for us. So if that schema ever changes, we just need to add a new column and then point it to that, and then it'll take care of that. Or if a column gets deprecated, you can still have it named in there, and it won't break when you go to query it. And so here's the assembled pipeline. So we bring that data in from Adobe Analytics. It lands in CSV with the manifest file as well. We transform that to Parquet using EMR. We land those files into our data lake in its pristine file format in Parquet. We then run an alter table command on that, which I haven't touched on yet, but I will on the next slide. And then we allow Glue to sit there and define the data, which then allows us to query it in Redshift. And so you may be thinking, well, why did you run that alter table command? So anytime that you partition tables, the data basically needs to be described in Glue. It needs to know that you've added another folder of data. So what you can do is you can actually run the crawler at whatever cadence you want. There's a number of different options. And that'll take care of crawling the data for you and describing it. The way that we did it is we actually had an Athena interaction class in Python that we built to interact with Athena. So we just added a method on top of that to our repair table. So once the job finishes in EMR, we'll just say repair the table and close the job. And so ever since we did this, this really showed us the benefit of having a data lake, and we got rid of a lot of the problems that we saw when we cast that data into Redshift, and it really made everything a lot easier. And so you can actually see we have an example here of our cycling log data. Because it was hundreds of millions of data points that were coming in, we actually used 2 different partitions here. So not only was it day, but it was also the facility that those bikes belonged to.
So we'll talk about a few other optimizations that we realized as building our system. So first off, a little bit about processing. So we do processing on Redshift, as we described. We do mainly our light transformation, the ELT scripts that we have built some orchestration around using our proprietary Maximilian framework. This happens inside of Redshift, but again, it's rather light crunches, transformation of data into final models. All of our big crunches and processing of semi-structured data happens outside Redshift and is either loaded into partition buckets, much like some of the data sets that Ryan described, or brought into Redshift as new tables. But we do that to really keep our Redshift cluster as small as possible and help preserve query capacity. So additionally, a lot of people want to know what our data models look like. Are they, star schemas, snowflakes, flat tables, somewhere in between a star schema and flattened tables. So our tables are flattened. We in Redshift, since it is columnar, it's okay to have really wide tables. You don't have to think about the same optimizations that you would for a row-oriented relational database. So we do that because columnar, it's okay to have wide tables, as well as distributed joins can be expensive. And we also use rational and conservative usage of dimensions as well. Like we have dimensions for our major master data elements, mainly for like a data management purpose. But in general, we try to reduce the number of dimensions. Basically, we just want to get the answer and put it in a table. And that's quite a relief if you've been building rigorous Kimball data warehouses for most of your life. So here's a quick example of one of our data models, one that you guys can probably figure out. It is our F check-in table. It is an event table which holds every time that a member visits one of our clubs. So it has about 300 million records in it. So as you'll see in one, we avoid creating dimensions we don't have to. So if you were like a Kimball guy, you'd be really tempted to create a terminal dimension with names and attributes and stuff that you'd probably never ever use. Here, we just flatten it in, and this is just pragmatism as well as the fact that Redshift doesn't mind being wider and from a table perspective. We resist other dimensional modeling temptations as well, such as creating junk dimensions. Like let's have a dimension which has attributes of the check-in. We flatten that into the fact as well. And we also avoid other miserable dimensional modeling concepts such as mystery or flag dimensions and bridge tables and stuff like that as well. We, you guessed it, flatten things into the fact. And again, it makes it really easy for our analysts. They don't have to worry about joins and strange tables they don't understand the structure of, as well as our developers. They can basically create the data set that they want to create, put it in a table, and figure out how to update that daily. So they don't have all that weight of dimensional transformation and key lookups and stuff like that. Oh, sorry.
And so as Lisa mentioned, Amazon's moving more and more towards a zero maintenance type of operation. So this is one of the things that'll be fully automated coming next year. In the meantime, I did want to share some of the optimizations that can be done through distribution keys and distribution styles. So just some information on the 3 different types. You have distile all, where essentially each node is receiving a complete table. And what this aims to do is reduce the disk usage for small and medium-sized tables. And this is really preferred for table sizes up to about 3 million rows on slow-changing data. The other 2 are distile key, where each node is receiving a portion of the data based on a chosen key. And what you're trying to do here is really optimize the performance of joins, insert intos, group bys, and commands like that. And then lastly, there's distile even, which essentially you're distributing the data in a round-robin style. And this you would use if neither option above applies. And so when it comes to decision time, I just want to highlight that it doesn't have to be between 3. What it's most likely going to be is a decision between 2. And that's really mostly just because of, is there a dist key available? If there is, then it's going to be between key or all. So if you're within that 3 million row mark, you're probably going to use all, and you're going to find the greatest optimizations there. Once you start getting past that, that's when you'll want to consider using key instead. And then if there is not a valid dist-out key, then you'll probably want to use all up until that 3 million row mark, and then use even thereafter. And if you're looking for a flowchart like this to help you with decision time, there's plenty on the blog, on the AWS blog that you can find. And so just some optimizations that we found with data lakes. Just want to highlight 5 of them here. So number 1, first and foremost for us, was leveraging self-described high compression Parquet files. Bringing in all of that Adobe Analytics data, that clickstream data, these are huge data sets that were coming in, and having them in CSV kind of worried us a little bit when it came to data storage. So if we could really leverage a high compression file format like Parquet, that would be huge, and so we were. Number 2, definitely use partitions where you can. So this is definitely going to reduce the amount of data that's queried, and it'll reduce the cost whenever you go to query that data as well. So you have faster, cheaper queries. But I just want to warn that you shouldn't over-partition. Even though you'll be querying less and less data, the more and more folders that you add, you're going to add some overhead in there. So if you're over-partitioning your data, your queries may actually take longer. Number 3 is lighten the compute load on Redshift when you can. Because that data is described in Glue, it can be accessible by many different query engines. So you can really leverage the power of Athena or EMR where appropriate. Number 4 would be ELT. So as we described earlier, we use this whenever we land our data into Redshift in order to make other tables in Redshift that have been joined together. What you can do here is you can actually say, data that's in S3, we can basically query that in Redshift, join it with some other Redshift data, and then save it back to S3. And so just by wrapping it in that unload statement, you've essentially done ELT from S3 to S3 without ever bringing it into Redshift itself. And just make sure whenever you unload that you make sure to compress. And coming soon, you'll be able to actually bring a Parquet file in and save it back to Parquet. And then easily perform delta queries. So for those mutable tables that we have in Redshift, sometimes we may want to perform a diagnostic analysis such as what changed. So if we bring those tables in to S3 and we unload those every day, we can actually query the tables against themselves maybe 2 days ago versus yesterday, and then say, okay, here's actually what changed between these two. That's great for diagnostic purposes. The other use case that we actually have for this is third-party services that want our data. They don't want us sending all of the data each and every day. So what we can do is say, here are the specific items that changed, and send them those.
So a little bit of a few optimizations that we've been able to do in automation and DevOps. So we're using some well-known tools in our pipelines, as well as we've built several platforms as well. So we've invested and built our own batch and DAG execution framework, which we'll hopefully be open sourcing soon, called Batchy. We have built our own data quality and monitoring system called Hambot, which is used to monitor the quality of our warehouse throughout the day, as well as used for automated regression. We've built other ops tools which help us monitor the data and just make sure that it's in good shape. We do all of our scheduling through Rundeck, along with our Batchy DAG execution engine, and we use Jenkins for our deployment operations. So a little bit about how we do deployments in a warehouse. So a few years ago, this would have been a completely novel concept, but a lot more people are starting to try to automate the deployment and testing of their warehouse. So essentially what we do is we have Jenkins workflows which are kicked off when everybody does certain actions against our Git repo. So essentially what we'll do is we'll go and spin up ephemeral Redshift clusters, EMR clusters, and assets from our repo in kind of like a clean room state. So we might restore a Redshift cluster which has specific fixture data that we have known outputs for. Or it might be that we're spinning up a cluster based on yesterday's backup. This is all automated, and it depends on the use case. We'll then go and run all of our major transformations from that branch, and then run a series of Hambot checks to assure that we are within domain norms, that we haven't created any data quality issues, and that nothing has changed that we didn't expect. And if all that works, we merge and deploy. Additionally, because AWS has like these great APIs, and we really wanted to empower our developers, now we can have as many Redshift clusters, EMR clusters as we want. We've actually created bots which allow our users to kind of interact with these services through Slack. You know, keep our admins and our sysops people from going crazy, spinning up infrastructure for these people to do development. So essentially they can go and start a cluster, kill a cluster, and really reduces the need for our tech ops as well as our users needing to have console access.
But every good guy bot needs a bad guy bot. And so we also built further ops interaction in Slack. And so this is a bot that's really looking for those clusters that people have brought up and maybe have left idle after, you know, work ended. And so what it does is a couple times a day, it comes to seek and destroy those clusters. You can intervene and say that you want to save a cluster. If you do, he'll ignore it. But if you don't, he'll actually tear it down. And so really what we're aiming to do here is save money on unused infrastructure and really, you know, take out the responsibility to have people go in and just check afterwards and bother everyone to say, you know, is this cluster, does it still need to be running? Can I take it down and have that conversation? He'll just come in and just blow it all away.
So a little on our results. So this has obviously been a really good experience for us. We're very happy with Redshift and S3 and our data lake strategy. So we're fully replatformed and productionalized. The first 2 apps which we brought live took about 4 months, which was that original app that we did in a POC as well as one additional. We finished our replatform in about a year. And you know, in general, we've just been very happy with the dependability. You know, we have very few operational issues. We don't have a Redshift DBA, and things are humming along pretty well. Something that we've really enjoyed is a faster time to benefit via automated regression. So one of the things we've done is obviously through the regression automation. So now we can release much more often and bring value to our business users much quicker without engaging a lot of QA resources. And obviously the huge cost savings over Teradata, so we're paying approximately 1/10 of what we were in licensing and maintenance alone. And it worked out so well, we decided to spread the love and build a new platform for Blink as well. We built them a brand new data platform, very similar to our own, using the same technologies, and it only took 4 months to completely replatform them. So in terms of the lessons learned, you know, so taking advantage of that S3 Redshift integration wherever possible, use an S3 approach wherever possible. So obviously if you have like this semi-structured data, this immutable data, definitely, and then just really, you know, think about how you can use that strategy because it has a number of benefits, including disaster recovery, access from many different tools, and so on and so forth. Develop an architecture which accommodates change. So this isn't just change in the data, onboarding new data sets. It's also embracing new technology. So Spectrum hasn't been around all that long. We saw that it could really help our architecture and, you know, solve problems for us. So, you know, we're quick to bring it on. One size doesn't fit all. Really think about the use case. Sometimes Redshift makes a lot of sense. It makes sense to actually physically copy that data and process that data in Redshift. Other times, Spectrum is a tool for the job, and other times, Athena is a good tool for the job. And then obviously, my last one is automate everything. So leverage automated testing, deployments, and take advantage of the kind of automation capabilities and APIs that AWS offers you to really modernize your data warehouse deployment. And that's all we have, and I'll just leave this slide up for a minute. Thank you very much.
Thank you.
Any questions?
We actually have a mic up here. Yeah. Go ahead.
Sure.
Fire away.
Right. So when you decided to go with your data lake approach and you moved to AWS, I would imagine you were introducing a number of new skills to your team. How did you go about that? Did you enlist the help of partners? What was that learning curve like?
Yeah, so we actually had a really cool experience with that. Someone from AWS actually came in and gave a presentation to everybody, so that definitely helped us a lot. But once we actually saw some success with it, it ended up becoming I guess like an evangelizing campaign from there. And so we try and have meetings with our team members as much as possible when new technologies are available. We kind of got a little bit lucky just because once we started putting some data in the data lake, there were other data sources that became available. And so other team members were able to go in and get their hands dirty with it.
Yeah, we found that the Postgres compatibility of Redshift was a big thing. The SQL was, for the most part, even when we're processing in Spark, we're wrapping SQL. People found the technologies pretty easy and pretty familiar. So we found a lot of our folks who were maybe traditional SQL developers didn't have that big of a barrier of entry. And then again, what Ryan was saying is people were really excited about the technology. They saw the wins that we had and some of the capabilities that these unlocked, and they were really excited to work for it. So we have probably a third of our team is now like AWS certified. So yeah, it's been great.
I have a couple of questions actually, but I'll just start with one and then leave to other guys. We are having a similar situation where we want to migrate Netezza to Redshift, and we are still yet to start POC, not yet, yet to start on that. So my question would be is like, I can understand the whole migration of this data into Redshift, but what is the other processes like Informatica ETL tool and then stored procedures? What are your insights? Like, how did you guys convert that? And then where did you place those scripts in S3 or like how you're calling, like
Sure.
insights into that?
Yeah. So one of the things you have is you have Informatica jobs and you have Netezza SQL, which is doing your processing, right? So we use Informatica only for lift of shift, and we're actually slowly getting away from that with our own internal platform. But in terms of the SQL, what we do is we store all of our SQL in a Git repository. And essentially our script runner, our Maximilian platform, takes those SQL scripts and essentially macros them to expand parameters and insert dates and batches and make them more dynamic. So we essentially have parameterized SQL scripts that we store in Git and then we run in workflows. So that's essentially how we process data. Could you come to the microphone?
So where are you calling that GitHub scripts from in AWS? How are you calling that?
Scripts in AWS, I'm sorry.
Sorry, so you have stored all the scripts, like scripts in the GitHub repository, right?
Yeah.
And that's your version control thing, and then you're going to call that from AWS, one of the services, right?
Oh, so how do we actually run this stuff?
Yes, it's from AWS.
Oh, okay. So all of our stuff is containerized, so we use ECS. So we have several containers, and we actually create containers in some case dynamically, but our main container is our rundeck container. So rundeck is just a scheduler. You could choose your scheduler. Mm-hmm. And we essentially pull all those repos local in that rundeck container, and then rundeck essentially executes within the container or outside the container by spinning up other containers. Kind of complicated, but essentially we have a Linux container where we issue, we use Python to orchestrate SQL scripts.
Sure.
Could be an EC2 instance, whatever you like. You could use cron and yeah.
Sure. So I'll let you guys like.
So as part of data quality, how did you maintain the data sanity in Redshift? As I understand, I'm pretty new to AWS, sorry, but so I understand that the Redshift does not really do a primary key constraint check.
Sure.
So how did you handle the data sanity as part of the data quality?
Yes, that's a good question. So first off, I'd say after building a lot of like really big data warehouses, first thing you do for performance is throw away all the constraints and stuff generally. But the way we handle it is through our data quality framework. So the things like relationship assertions and lack of duplicates are all handled in our data quality system. So after a load, we essentially, we'll do an assertion. Do we have duplicates? Do we have missing data? Do we have relationships that don't work? If we do have tables that will join together. So we essentially would load, then run the assertions and either block downstream processes, ring PagerDuty for some engineer to look at. So essentially, we handle it post-load. And we also do inspections up front as well. So if we have data in S3 that we're not so sure about, or data that comes in from our various systems that we pull down into Redshift or S3, we'll run assertions on that through Spectrum or through Redshift to essentially see the quality of the data before we go and load those downstream models. Does that make sense?
Yes. So I think so I'll catch up with you after the meeting.
Sure, sure,
I don't
absolutely.
want to take-
So why did you choose to do the Maximilian proprietary data platform thing instead of going with something like Glue?
Yeah, that's a good question. So we started this, I think, before Glue was created. Glue's also primary execution engine is Spark, right? So some of our workloads are very small. We're interacting with various like relational data sets. So it made sense to us to just be able to massively parallelize, pulling data from relational databases through our own framework. Plus, we have a lot of features in there, not just moving data, but also orchestration and so on and so forth. So it's more than Glue. I'd say it's like Glue plus Luigi plus, a lot of other, kind of execution frameworks and automation frameworks.
Thank you.
No problem.
Hey, how did you deal with Teradata stored procedures? Did you have any BTIC or any of the sort of the Teradata specific?
Yeah, so when we moved those apps from Teradata, it was a rewrite. We weren't able to use the modeling techniques that we'd use in Teradata, that you model the data in a specific way, nor the Teradata SQL. We just essentially used the business logic and a lot of the kind of modeling and kind of requirements that we put into that Teradata work to inspire the work that we did moving to Redshift. So it wasn't directly usable in our case.
I see. So you didn't actually have to convert any Teradata SQL sort of,
No, we just greenfield it. So we just started from scratch. It was easier, but we used the Teradata for SQL for guidance, in terms of the business logic. Like in a lot of cases, it's SQL. The calcs are the calcs. It was really like, what's the model that we're loading? What are the specific techniques for processing the data? Okay. Oh, you got time.
So I just want to add one point. As of in the morning, what I heard is like Redshift is going to support stored procedures starting
Yeah.
first quarter of 2019.
Soon. So,
So
that should be easier.
Is it up in the air? Is it?
It's going to be coming soon in the
first
next
quarter.
few months, first quarter.
Yeah, like that's like very happy news for me.
I think, happy news for everyone.
ELT stored procedures for us. So that's a big relief where we don't have to really split those things up and then look out for services on AWS to really split that stored procedures. So that's a savior. So coming back, I heard something about ELT approach where you're taking stuff on S3 and then doing something back on Redshift and putting back into S3, right?
Mm-hmm. Yes, the question was, how are we doing that?
Yeah, you said something, you're doing ELT
Right.
from S3 and then
And sending it back to S3?
inserting back to S3 and then the operations is happening in Redshift, right?
It could be, yeah. The way that we're actually doing it, so for instance there, the specific use case was we had our clickstream data that was coming in, but you really had to be a pro if you wanted to query that effectively. And so, there were conversations that we had to have with our analysts where it's like, oh no, you need to make sure it's this specific ID or it's that specific ID. And so what we ended up doing there is we said, let's bring in that data and then summarize it. So we actually summarized it by each visit that everybody has, by every day, and by every month. And so we ran those scripts in Redshift and did an unload. So we ran those scripts, did an unload, basically summarized the data, and then put it in another section in our data lake. So now what we do is we say, oh, if you want to analyze the data, just go to the summary data, because that takes care of a lot of the logic that's kind of nuanced about clickstream data.
And this was, in this case, could have been accomplished through a Spark job or a Hive job or something externally. But the ease of use and the fact that when you do run S3 only queries, it's mostly taken care of in Spectrum. it created a very light load on Redshift. So we decided to do it for convenience and, started out as a quick win for our analysts.
So you're not
community.
using any complicated joins on S3 files, right?
No, it's just the clickstream
Pacing,
data.
summarization, it all gets processed on Spectrum for the most part. And I would come back to the stored procedures just real quick. We may or may not accept that because we have really started to like, having that integration with Git and being able to manage branches. The first thing that happens when you start putting stuff in the database, nobody tracks changes anymore, et cetera, et cetera.
I would definitely love that point because I'm going to do the exact same thing, but because there's tons and tons of code, like to start to prove that Redshift works, I need to prove something, right?
Yeah,
So
so
that's
we're,
the starting point. And one question, you're talking about resizing on Redshift, right?
Yeah.
Is that going to repartition the data on the new nodes?
Sorry, what was the question?
So there are like 4 nodes. Let's say that there's a 4-node cluster on Redshift. I'm pretty much new to Redshift, so I might ask dumb questions. But so there's 4 nodes cluster on Redshift.
Okay.
And because of the scale, you're gonna increase that to like 2 or 3 more nodes, right? So certain tables, most of the tables, because Redshift is exactly like Netezza, so I can exactly borrow all the experience what I have in Netezza. So data is like pretty much partitioned for a good joins or for the easiness of the complicated joins. Now that the data is partitioned on those 4 nodes based on the hash algorithms, adding like 2 more nodes, right? So I don't know, like it has to repartition the data, right? It has to move the data back.
I guess we'll rebalance those partitions
those.
across.
So,
If it's
yeah,
a
it will
huge data-
rebalance. It will rebalance those partitions. So it
And,
will reconfigure all of the data, and it will be rebalanced.
And that shouldn't be any bottleneck, right, while doing so?
Sorry?
That wouldn't be a bottleneck while doing so because...
No, it should not be a bottleneck.
Okay.
And Elastic Resize is available today, so you can start trying it out now.
Sure, thanks.
Yeah, of course.
We're out of time. Thanks, guys.
Great. Thanks, everyone.
Thank you so much.